Today we're going to be talking about the fundamental trig identities. By the end of this video, you should be able to use the 25 fundamental trig identities, you should be able to factor trigonometric functions, and you should be able to simplify trigonometric expressions. So first, let's take a look at 5 different categories of trig identities. The ones on this slide you have seen before. You know that cosecant is the reciprocal of sine. Well, that also means that sine is the reciprocal of cosecant. Similarly, secant is the reciprocal of cosine, so cosine is the reciprocal of secant. Cotangent is the reciprocal of tangent, so tangent is the reciprocal of cotangent. You have also seen the quotient identities before. You know that tangent of theta equals sine of theta over cosine of theta. And since tangent and cotangent are reciprocals, that means that cotangent of theta equals cosine of theta over sine of theta. We have discussed the Pythagorean identities before. The main identity is sine squared theta plus cosine squared theta equals 1. And as we discussed in a previous tutorial, if you divide this identity by cosine squared, you'll end up with the second identity here. Tangent squared theta plus 1 equals secant squared theta. And if you divide this by sine squared theta, you end up with this third identity here. Cotangent squared theta plus 1 equals cosecant squared theta. The important thing to remember about the Pythagorean identities is that you will frequently see them rewritten. For example, I could solve this first identity for sine squared and have sine squared theta equals 1 minus cosine squared theta. You need to recognize that this is just rewriting sine squared theta plus cosine squared theta equals 1. You could also rewrite this as cosine squared theta equals 1 minus sine squared theta. So please recognize that these can be rewritten and they are just different forms of the same identity. The new identities that we're going to look at today are the cofunction identities and even and odd identities. So the cofunction identities have to do with the graphs of the trig functions. We have sine of pi over 2 minus theta equals cosine theta. We discussed when we looked at graphs of trig functions that sine and cosine are just shifted horizontally from each other. So if we take a look at a graph, I have here the graph of sine of x using the same dimensions for the graph as we did when we were graphing. Here I have the graph of cosine of x. If I shift the graph of cosine of x pi over 2 units to the right, I would have the graph of sine of x. So you can see here this third equation is that cofunction identity. So when I turn this equation on, it will line up exactly with the graph of sine of x. And you can look at any of the other cofunction identities and their graphs, and you'll see the same thing, that they are just phase shifts of one another. One memory trick that you can use to remember which functions go together is this is called cofunction. Sine goes with cosine. Secant goes with cosecant. And tangent goes with cotangent. Next, we have the even and odd identities. We discussed even and odd functions earlier in the year. Cosine and secant are considered even identities. When you take negative theta and take either the cosine or the secant of that angle, that is the same as cosine or secant of the positive angle. As we discussed earlier in the year, even functions are symmetric over the y-axis. So if you look at the graphs of these functions, they are symmetric over the y-axis. The other four functions are odd. If you take sine, cosecant, tangent, or cotangent of negative theta, then that is the same as negative sine, cosecant, tangent, or cotangent of the positive angle. Remember that odd functions have rotational symmetry around the origin. So if you look at the graphs of those functions and rotate the graph 180 degrees around the origin, you still have the same graph. Now, as we are simplifying trigonometric expressions and we get farther into verifying trig identities, here are some strategies to help you figure out these problems, because the problems can have a puzzle-like feel. Substitution is frequently helpful. Use the identities, try to substitute part of the identity in for something else in your expression. Factoring can be helpful, which we'll take a look at in a minute. You can combine or separate fractions. You could rationalize the denominator or sometimes rationalize the numerator. Changing everything so that is in terms of sine and cosine only can sometimes be helpful. But the most important thing is to try something. If you end up at a dead end and you have to start over, that's okay. But you need to try something and you might end up figuring it out after you've tried to simplify the expression. So let's take a look at a few examples. First, we're going to look at factoring. We have secant squared of theta minus 1. Well, if you remember from factoring, one of the things that we looked at was factoring the difference of perfect squares, which is the situation that we have here. So I'm going to rewrite this as x squared minus 1, because I have something squared minus 1. You should remember that this factors to x plus 1 and x minus 1. Well, this is the same situation. We have a perfect square minus a perfect square. So secant squared theta minus 1 factors to be secant theta plus 1 and secant theta minus 1. If you have a hard time seeing how to factor that and you want to change it so it looks more like a Algebra 1 or Algebra 2 problem and rewrite it with an x instead of a secant, that's totally fine, but that is not required. Here we have 4 tangent squared theta plus tangent theta minus 3. Again, I'm going to take these tangent thetas and change them to x's. So this is the same as if I had 4x squared plus x minus 3. Now there are many different methods that can be used to factor quadratics like this one. You could use trial and error method, you could use the box method, you could use factoring by grouping, or one of the many other factoring methods. I'm going to do trial and error. So I know that the first two terms need to multiply to 4x squared. The last two terms need to multiply to negative 3. And when you double distribute, this times this and this times this need to add up to x. Well, 3 is a prime number, so I know that the only options are 3 and 1. One of them has to be positive, one of them has to be negative, and I'm not sure which one that is yet. 4 is not a prime number, so I could have 4 times 1 or 2 times 2. In my thinking, as I'm trying to do this, I know that I have to get this to add up to positive x in the middle. So if I have 4 times 1 and 3, and the 4 is positive, the 3 is negative, I'll end up with positive x as my middle term. If you have trouble following this and you want to use one of the other methods to factor, go right ahead. But once you have this figured out, then you know your factors for our original trig function. Our factors will just be 4 tangent theta minus 3 and tangent theta plus 1. If you want to double check your work, you can always multiply the factors back out. Lastly, we have cosecant squared x minus cotangent x minus 3. Here we have two different trig functions, so we cannot simply factor the way we did on the first two. We need to look at our identities and see what we can change. I see a cosecant squared here, so I'm going to go back to my Pythagorean identities and see what we can do. Well, cosecant squared theta is cotangent squared theta plus 1. So if I do this substitution, that would give me all cotangent, and then I can factor. So I'm going to substitute cotangent squared theta plus 1 for cosecant squared theta. So instead of cosecant squared x, I have cotangent squared x plus 1. And then I'm just going to bring down the rest of the function. Then I can combine like terms. Now I'm ready to factor. So now I have cotangent squared x minus cotangent x minus 2. That is the same as if I had x squared minus x minus 2. We need to find two numbers that multiply to negative 2 and add up to negative 1. So that would be negative 2 and positive 1. So now I know that my factors are going to be cotangent x plus 1 and cotangent x minus 2. Now let's look at simplifying some expressions using our identities. There is not one correct method for simplifying these. For most of these problems, I'm going to show you two different approaches. There are other approaches that would work as well. But whatever you see first in this expression, go ahead, substitute with your identities, and try to simplify. So I have sine x times cosine squared x plus sine of negative x. Well, this sine of negative x is going to be an issue. So I'm going to go ahead and use my even and odd identities. I know that sine of negative x is the same as negative sine of x. So now I'm going to show you two different methods to simplify from here. First, I'm going to start by factoring out a GCF. So if you look at this expression and the first thing you see is, hey, I can factor a sine x out of both of these terms. Then you would follow this method. So if I factor out a sine of x, so now you want to look at what we have here and see if you can use another identity. This part in the parenthesis looks similar to one of our identities. So we have cosine squared x minus 1. Let's go back and look at our identities. If we look at this first Pythagorean identity, we have 1 minus cosine squared of theta. Our problem has cosine squared of x minus 1. So instead of being equal to sine squared theta, it's going to be equal to negative sine squared theta. So we can do that substitution. And then we just multiply to get negative sine cubed x. If we go back here and you don't see that you can factor out a GCF, that's okay. You might see this cosine squared and think, let's do substitution. So if we look at the Pythagorean method, so if you see cosine squared x first, and you want to go ahead and substitute for that, we're going to look at this rewritten version of the Pythagorean identity. So we have 1 minus sine squared x. So then we want to distribute. So we have sine of x minus sine cubed x minus sine x. The sine of x and negative sine of x cancel out, and we just have negative sine cubed of x. So you can see that you get the same answer regardless of what step you choose to do first. Whatever you see when you look at this problem, go ahead and do that first. Let's look at another example. Here we have sine of alpha plus cotangent alpha times sine of pi over 2 minus alpha. Well, this is one of our cofunction identities. You can see that sine of pi over 2 minus theta is equal to cosine of theta. So let's go ahead and do substitution. So we have sine of alpha plus cotangent alpha times cosine alpha. Now I'm going to go ahead and change everything to be sines and cosines, which means I'm going to rewrite cotangent using our quotient identity and rewrite this as cosine of alpha over sine of alpha. So now if I go ahead and multiply, I have sine of alpha plus cosine squared of alpha over sine of alpha. Again, from this point, there are two different paths that we could take. Well, there are two different paths that I'm going to show you. There are probably more than that. So I'm going to start by combining the fractions. So that means I need to get a common denominator. So I need to multiply this first fraction by sine of alpha over sine of alpha. So then I'll end up with sine squared of alpha plus cosine squared of alpha over sine of alpha. Well, sine squared alpha plus cosine squared alpha is one of our Pythagorean identities, and that is equal to 1. So I have 1 over sine of alpha. And then we know that 1 over sine of alpha is equal to cosecant. Then we know that 1 over sine of alpha is equal to cosecant alpha. That's not the only way we could have simplified this problem. If you look here and you immediately see this cosine squared of alpha and you want to do something with that, you could start with a Pythagorean identity. So if you start with substituting 1 minus sine squared of alpha for cosine squared alpha, here's what you get. We have sine of alpha plus 1 minus sine squared alpha over sine of alpha. Then you can split up this fraction. And I get 1 over sine of alpha minus sine squared alpha over sine of alpha. Then I just need to simplify. One over sine of alpha is cosecant alpha. Sine squared alpha divided by sine of alpha is just sine of alpha. So then I have sine alpha minus sine alpha, those cancel out, and I just end up with cosecant alpha. Regardless of what pops out to you in this expression here, if you continue simplifying, you'll still end up with the same answer. Let's do one more problem. Here we have sine of theta over 1 plus cosine theta over sine of theta. Because we have two fractions and it's all sines and cosines, I'm going to go ahead and get a common denominator. So that means I need to multiply this fraction by sine of theta over sine of theta, and this fraction by 1 plus cosine theta over 1 plus cosine theta. So then I end up with sine squared theta plus, I'm going to distribute this cosine theta plus cosine squared theta. And then my denominator, I'm going to go ahead and leave it as sine of theta times 1 plus cosine theta. Now, I see sine squared theta plus cosine squared theta, and I know from my Pythagorean identities that that is equal to 1. So I just have 1 plus cosine theta over sine theta times 1 plus cosine theta. Since I have 1 plus cosine theta in both the numerator and denominator, I can cancel those out. So I end up with 1 over sine theta, which is equal to cosecant theta. So remember that the key to simplifying trig expressions is to try something. I gave you a list of strategies earlier in this video. Try to substitute something from your identities, do some algebra to factor or combine fractions or separate fractions. Just try something. It is a little bit of a puzzle.